of glycolysis. And I was kind of like wondering how I should format and study for this biochem test. This is the first one of the semester, and I was thinking of doing like short videos that were just going specifically over the reactions, and then I'll just like type out my notes that the teacher was lecturing over, and then trying to condense them into more manageable form. So I'm going to probably do like a short video on the reactions themselves, like all the steps, only going in detail when needed, and then later on is like the rationale and like the actual notes. All right, so glycolysis, this is the reaction 6 glucose plus 2 of NAD, ADP, and inorganic phosphate. After the steps, you're going to get 2-pyruvate, which is a 3-carbon sugar. So we're going to have glucose, a 6-carbon, going into a 3-carbon. 2-pyruvate plus NADH plus H plus ATP. Okay, so again, glycolysis, breaking down glucose. So step 1 through 5 will be our prep phase. And step 6 through step 10 will be our payoff. We're going to have a net gain of, again, 2-pyruvate, and the most important part will be the 2 ATP. We say net gain because we're actually going to have to spend 2 ATP in the prep phase, but we're going to have 4 technically because of the 2-pyruvate. And when we're using that process again, we're going to be balancing it out, so a net of 2 ATP. All right, step 1 in the prep phase. Going to just switch. Let's do. Okay, yeah, prep phase. Glucose to glucose 6-phosphate. That 6 determines that we're going to put that phosphate on the 6th carbon. We're going to be using the enzyme hexokinase. And this is irreversible. This is the first irreversible step. There's going to be 3 irreversible steps in glycolysis. Number 1 is one of them. We'll get to the others later on. Okay, the rationale of this is to trap the glucose inside the cell. Since glucose was originally nonpolar, by making it have this 6-phosphate on its 6th carbon, we're going to be able to give it a charge, so therefore it stays inside the membrane of the cell. It's not able to go through that uncharged area or slip through. Therefore, since we're going to trap glucose in the cell, this will actually allow for more glucose to be brought in. All right, step 2. I said we're going to go through these pretty quickly, but step 2, this is going to be glucose 6-phosphate, and it's going to be transformed into fructose 6-phosphate. Right, so glucose and fructose. We're going to be changing an aldose, which is glucose, into a ketose. Fructose is a ketose. We're going to be using phosphohexose isomerase. That's the enzyme. I'm going to probably circle the enzyme. So glucose 6-phosphate to fructose 6-phosphate, we're going to be using phosphohexose isomerase. Isomers, again, are going to be the aldose and the ketose. So fructose, again, is a ketose. We're going to be using an isomerase. Phosphohexose, that means a hexose is a 6-carbon sugar, and then it has a phosphate on it. So there you go. And the important part of this enzyme is we have this glutamate. That's the important amino acid there. It's a specific group that looks like a carboxylic acid, and its charge. Those are going to be important, so that's the important amino acid of that enzyme. The rationale for this is to have easier carbon-1 steps later on. And we're going to have a symmetrical cleavage of the aldyl. We want to make sure it's as simplified as possible, so we need a symmetrical molecule when we're going to cleave it later on. All right, step 3. This is fructose 6-phosphate, which is going to now transform into fructose 1,6-bisphosphate. So fructose 1,6-bisphosphate. Could write it out. We have space. All right. The enzyme here is going to be phosphofructokinase. Kinase again means we're going to be transferring a phosphate. And this is phosphofructokinase 1, also known as PFK1. That -1 there is very important. Do you see how there's a 1 here? They're related. There is a fructose 2,6-bisphosphate. However, that molecule isn't part of this reaction other than being a regulator of this step. When we have that fructose 2,6-biphosphate, this is going to drive the reaction forward. Again, when we get to this PFK1 step here, step 3 in glycolysis, this is going to be irreversible. Our previous irreversible one was step 1, but now step 3 is also irreversible. And we're going to circle the enzyme. Okay, so the purpose here is to activate glucose. Continue activating the original molecule here, where it's being transformed and it's getting more activated. All right. Step 4, we're going to take our fructose 1,6. Again, 1 is part of the reaction as a product and then a reactant in step 4. Fructose 1,6-bisphosphate will be transformed into 2 molecules here. We're going to have dihydroxyacetone. Sorry about that. Running out of space. Dihydroxyacetone phosphate, as well as glyceraldehyde 3-phosphate. It's going to make both of these because the enzyme that we're going to be using here is going to cleave this bisphosphate, this fructose 1,6-bisphosphate. This is an aldolase. It's going to cleave it into these 2 molecules, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. The purpose, again, of this cleavage is to create these 3 carbon high-energy molecules. And we're going to make 2 kinds. So there's a problem here. We're making 2 kinds of these high-energy 3-carbon molecules, but we would like to, again, streamline this process as a cell. So we have step 5, and this is the last step of the prep phase. We're going to actually transform our products here so that dihydroxyacetone phosphate, also known as DAP, we're going to just transform it into GAP, or glyceraldehyde 3-phosphate. We're going to be using this enzyme called the triose phosphate isomerase. Again, they're isomers of each other, DAP and GAP, so we're just going to go into the other isomer. So now we technically have 2 GAPs. One that was originally a DAP, and then one that was GAP at the start. When we get here, we're going to have a single payoff reaction. Again, we streamlined it, so we're in good hands right here. Okay, so that was the prep phase. Now let's talk about the payoff phase. Number 6, step 6, we're going to take our gap. And again, this is going to happen technically twice. There's going to be 2 runs of this because we have 2 gap molecules, but I'm just going to mention it as one right here to, avoid overcomplicating things. All right, so our glyceraldehyde 3-phosphate is going to be transformed into 1,3-bisphosphoglycerate. All right, so something interesting about this molecule here, it does have this bisphospho, but it's a different number here. So fructose 1,6-bisphosphate was earlier. It's step 3, and it's part of the prep. However, 1,3-bisphosphoglycerate, glycerate at the end there, and 1,3 at the front. This is going to be step 6 of the payoff phase. All right, the enzyme that we need here is going to be GAP dehydrogenase. GAP dehydrogenase is going to take off, again, an H because dehydrogenase. So we're going to dehydrogen, basically, this gap. And when we do that, we also get our NADH. This is reduced. This is the reduced form of NADH. That's going to be useful later on when we need this reducing power or an electron carrier, so that's a good thing we made that. Okay, number 7, step 7. We're going to be doing 1,2,3,1,3-biphosphoglycerate. And it's going to be transformed into 3-phosphoglycerate. All right, something cool does happen here. So at step 7, we're going to be doing something called substrate level phosphorylation. Whenever we do substrate level phosphorylation, especially in this reaction, step 7 of glycolysis, we're actually going to be able to make some ATP. So we have our first instance of making ATP here. The enzyme that we're going to be using is a phosphoglycerate kinase. Kinase, again, transfers a group. And actually, let me see. Yeah, a kinase. I think I wrote it down here. Let me see. 3, sorry about that. I'm just checking something. Okay, so we got substrate level phosphorylation. I kind of got lost in my notes. I think I forgot to add the rationale there, so I'll do that in a bit. All right, so phosphoglycerate kinase again. 1,2,3-biphosphoglycerate to 3-phosphoglycerate plus ATP. That's the important part. The rationale is substrate level phosphorylation, and we could also add the rationale for step 6. Again, we need that inorganic phosphate. That's what I forgot. So step 6, we're going to also introduce an inorganic phosphate. We need that later on for step 7. And again, we have a high energy molecule. All right, step 8. We went over step 6 and 7, kind of had to backtrack there, but I think we're in a good position. Step 8, we're going to take that 3-phosphoglycerate and we're going to transform it into 2-phosphoglycerate. We are going to be using a phosphoglycerate mutase. As the enzyme. The purpose here is to transfer the 3-phosphoglycerate to a 2-phosphoglycerate. That's just going to be a different carbon. We're going to increase this high energy molecule here by working with the 2 instead of the 3rd carbon. So the rationale would be a high energy molecule would have interactions at the 2 instead of the 3. All right, step 9. We could also go deeper into these rationales when I do the next video on the notes for glycolysis. All right, 2-phosphoglycerate will transform into phosphoenol. There's a reason why I'm writing it like this, pyruvate. All right, this molecule here, phosphoenolpyruvate, is also known as PEP, so that's why I kind of stacked them up like that. When we're going here, we're going to use the enzyme analase. And this is going to be a high energy molecule again, so kind of the same rationale, just making it have even more energy for us, continuously transforming it. All right, number 10, this is the last step of the payoff phase. We're going to have that phosphoenolpyruvate. We're going to transform it to our regular pyruvate. Remember, the net will be 2 copies of this. And we're also going to get our last ATP here, our last set of ATP. Not AP, this is not an AP class. Stop writing that. Okay. All right, so this is also irreversible. And the enzyme that we're going to be using is pyruvate kinase. This is again a substrate level phosphorylation event. And got through all the steps. We got to our end here. We also have tautomerization in step 10, but main point, substrate level phosphorylation. We made our final thing of ATP, and we got through glycolysis. Should I talk about the regulation in this or no? I guess we can. All right, so let's talk about the regulation in glycolysis itself. So we got through all of that. We made our 2 net ATP, our 2 pyruvate. This is again a 3-carbon molecule that could be used fermentation or the citric acid cycle. ATP again, we made a net of 2 as well. Okay, so other molecules in glycolysis, you could also have glycolysis of the endogenous glycogen to go to glucose 1-phosphate. This will require something called the phosphorylase enzyme. And then after that, could go here. I'm going to title this other molecules. All right. Once we get to our glucose 1-phosphate, we need to now get to glucose 6-phosphate in order to continue in the pathway. So the enzyme here, our second enzyme when we're using endogenous glycogen, sorry about that, we're going to be using a phosphoglucomutase. Another molecule that could be used in glycolysis would be the dietary glycogen. Dietary glycogen goes to glucose in a whole slew of steps, but the most important would be the enzyme alpha amylase. We also have a few other molecules, but 2 of them are the focus. we have lactose and sucrose. They also make another product other than just glucose, but lactose will use lactase, so I'm going to just write ace at the end there. Sucrose, similarly, we'll just use sucrase, so the enzyme there is kind of sharing a name with the reactant. Right. There is another regulation in glycolysis and kind of in gluconeogenesis. It's kind of back and forth. So we were talking about step 3. So step 3 was the second irreversible step here. Involved the PFK1. So with our regulation, we're going to be talking about this. This is a regulation step in glycolysis. I'm going to just paste it back here so we could work with it. All right, for review, step 3 in glycolysis is fructose 6-phosphate. Goes to fructose 1,6-bisphosphate when we have phosphofructokinase 1. But we also talked about fructokinase 2, so that's going to involve this fructose 2,6-bisphosphate. So we're going to be increasing this forward when we're stimulated by, again, PFK2 and insulin. PFK2, let's talk about PFK2. PFK2, I'm going to write regulation. PFK2 is basically combined with this other enzyme in gluconeogenesis. They're on the same molecule there. But PFK2, just write that here, we're going to be going from our fructose 6-phosphate to fructose 2,6-bisphosphate. When this happens, we're going to be increasing or driving forward glycolysis, aka the phosphofructokinase 1's activity. We do this in the presence of insulin as well. On the flip side, we could actually go backwards here when we're going to talk about gluconeogenesis and more regulation, where we're going to be going from F2,6-bisphosphate to fructose 6-phosphate, so basically going back one level. We're going to have a phosphorylated section of this same molecule. So again, this is split up because there's two basically enzyme functions on this one molecule. There's the phosphate fructokinase 2, and then on the other side, on the flip side, we have the fructose biphosphate 2,6, and 2, and when it becomes phosphorylated, when this becomes phosphorylated, and when glucagon, which basically is a stand-in for like glucose is gone, so we need to make more. So glucagon, and when this F2,6 biphosphatases are phosphorylated, this is going to actually change it back to fructose 6-phosphate. That's regulation. All right, those were the steps in glycolysis. Please do something nice for someone and have a good one.